Hello, and thank you for stopping by. This video will serve as an introduction and explainer to the Automunge platform for tabular data feature engineering. We expect that given some of the fundamental territory that Automunge covers in the machine learning workflow, this tutorial may also be useful as an educational resource for those looking to gain some vocabulary and insight for the basics of machine learning practice. Oh, and as a heads up, our graphic design team really went all out on the special effects in this video, so please prepare to be wowed. But first, before we get to all the special effects, here's a kind of Reader's Digest summary. Automunge is an open source Python library, available now for pip install. As a Python library, it's intended for use by data scientists comfortable with working at the coding layer, such as in the context of Jupyter notebooks, without the support of a graphic user interface. Not to worry, it's very easy to use. By passing the Automunge function a NumPy array or pandas data frame, the function automatically converts to numerical encoding and infills missing values, thus giving a user means to pass raw data directly to a machine learning algorithm. But a user doesn't have to defer to automation. The tool also serves as a platform for feature engineering, which for those unfamiliar with the term feature engineering just means data transformations intended to make some stream more easily digestible by machine learning. We have a whole library of data transformations available to be assigned, and a user may also pass their own defined transformations within the platform. Oh, and we'll get to this in a bit. We also have some pretty nifty methods to predict infill to missing or improperly formatted points by making use of machine learning, what we call ML infill, and so much more. All of this functionality is available through the application of two simple functions: Automunge for the initial preparation of tabular data for machine learning, and postmunge for consistently preparing additional data. In fact, an important point to keep in mind as we progress in this video is that most of what we're going to demonstrate here is available by activating just a single parameter in one of these functions. It's all push button and automatic. The workflow of preparing data with Automunge is pretty easy to visualize. After importing and initializing the class, such as in a Jupyter notebook, we simply pass a NumPy array or pandas data frame of the tabular data we intend to use to train a machine learning algorithm, what we'll call our train set, and optionally, if available, a consistently formatted set that we intend to use to generate predictions from the algorithm, what we call our test set. The Automunge function returns a series of sets including prepared training data, validation data, and test data, each further segregated by training features, labels, and index columns. And by prepared, we mean numerically encoded, with infill to missing values, such as to be suitable for direct application of machine learning. Importantly, the Automunge function also returns a Python dictionary which serves as a key for consistent processing of additional data. Once we have that key, we can then pass any additional data to the postmunge function to return consistently prepared data, with no external database required. Everything we need to consistently prepare data is embedded in that return dictionary. Okay, let's back up for a second and talk about the kind of data that we're passing to these functions. One way to categorize datasets could be the shape describing the number of dimensions of data point entries. For example, a scalar would just be a single value, such as the number 1, and then that also has a shape of 1, meaning 1 dimension. If we then assembled a list of scalars, this could be described as a vector, such as a set of measurements for a single variable, and the shape would just be the number of measurements. Here we show 3 measurements. If we then aggregate multiple vectors into another list, such as a list of lists, that can be described as a matrix, with the shape having 2 entries for number of rows and number of columns. Oh, and if we continue to embed lists within lists of lists, this type of higher order aggregations are known as tensors. One example of a tensor dataset could be like a collection of images, each with their own aggregation of RGB pixel values. But let's not get distracted by higher order tensors, because it turns out that the matrix style of data, also known as tabular data or structured data, is a very common grouping. And in fact, one way to think about Automunge is that it is a tool explicitly intended as a means for preparing tabular data for machine learning. So let's take a closer look at a tabular dataset for a machine learning project. Again, by tabular, we just mean a table of data with rows and columns, such as data found in an Excel spreadsheet, a Pandas data frame, or a NumPy array, for instance. One of the only prerequisites for Automunge is that data be received in a tidy form, which just means a single column per feature and a single row per observation. This example table represents a set of features or properties of small animals, which we would like to apply to machine learning for predicting classifications of whether that animal is a dog or a cat. In order to train a machine learning model, we'll need a set of features and a corresponding set of labels, which we will use to algorithmically infer relationships between the features and labels. But in order to train the machine learning model, we'll first need to perform some preparations, such as numerical encoding, normalizations, and infill to missing points. Basically, all the stuff that Automunge is for. In practice, once we have our training data prepared, we'll often segregate into two or more sets, one for use to train a machine learning model, and the other to validate that machine learning model and tune hyperparameters. Once we have trained our model, we can then use it to predict classifications of unlabeled data, demonstrated here for what we're calling our test data. An important point to keep in mind is that any data transformations that are applied to the training and validation data will need to be consistently applied to the test data to run the inference operation. But before getting into that, let's take a closer look at the workflow associated with training a machine learning model. Once we have our tabular dataset prepared for training with Automunge, we can then feed our training data sets of features and corresponding labels to train a machine learning model, which could be any of the multiple options to choose from for tabular data, such as neural networks, decision tree methods, and etc. Once we have trained a machine learning model, we can then use the validation set that we had carved out from the training data to evaluate the accuracy of that model. Such validations can be used to iteratively tune the parameters of the training operation, such as to improve model accuracy. Oh, and not shown here, it may also be appropriate to carve out a second validation set, one not used in hyperparameter tuning, to estimate accuracy of the final model. Having trained a model, we now have the ability to pass that model unlabeled data to infer labeled predictions. Of course, the model operates on the assumption that this unlabeled data is consistent in form and distribution to the training data used to train the model. So any data preparations that were applied to the training data with the Automunge function must now be consistently applied to the test data with the postmunge function. The application of the Automunge and postmunge functions in this workflow is now depicted. Automunge, here abbreviated as AM, receives a raw dataset which may not be ready for machine learning, such as, for instance, not fully numerically encoded or having missing data points requiring infill. Through the application of the Automunge function, that data is segregated into training and validation sets, each consistently prepared with feature engineering transformations and infill for ingest by the machine learning training operation. Just as how the machine learning training operation returns a trained model that is used to infer predictions, the application of the Automunge function returns a trained dictionary capturing all of the steps and parameters of transformations that can then be used to consistently prepare additional data with the postmunge function. Shown here, consistently converting additional raw data to a test set for use to feed the trained model and infer predictions. So let's talk about what we mean by preparing data for machine learning. It turns out that mainstream machine learning libraries have a few prerequisites of data for training a model. First, the data will need to be numerically encoded, meaning raw numbers with no units or strings in the representation. There are some libraries that allow a user to designate categorical sets for internal representation of past strings, but that extra intervention is not required as long as data is directly served in numerical encodings. Another common type of feature engineering involves the normalization of numerical sets. Think of this as like scaling and centering the set of values within a designated range. Now, not all machine learning algorithms uniformly benefit from this step. For example, neural networks have a much more pronounced benefit from normalization than decision tree methods, for instance. There are some types of algorithms which require all positive values, in which case a type of normalization may be a firm prerequisite. Since the application of normalization here is push button and automatic, we recommend just defaulting to normalization of numeric sets. Another prerequisite for training is that the datasets must contain all valid entries. It is common that real-world datasets may have instances of missing or improperly formatted entries. In the Automunge library, every transformation function includes a default method for infill, and alternatively, a user may also designate specific means of infill to distinct columns. The prerequisite shown here of data pipelines simply means that whatever transformations we apply to our training data, we will need to consistently apply to subsequent data used in the inference operation to generate predictions. The Automunge library makes this as simple as can be, as subsequent consistent processing is achieved with just a single function call to postmunge, using the return dictionary from Automunge capturing the steps and parameters of transformations. Another point of value that we'll briefly highlight is that in some cases, a training operation may benefit by presenting our feature sets to the algorithms in multiple configurations, such as with varying information content. This might not be as important when a user has access to infinite training data, but when faced with limited data, presenting feature sets to the machine learning algorithms in multiple configurations may facilitate more efficient extraction of properties for deriving relationships between training data, features, and labels. When we talk about performing feature engineering transformations to the columns of our datasets, it's worth highlighting there are a few ways to go about this. Although some transformations can be performed independent of the dataset contents, most transforms require first extracting some properties from the data to use as a basis for transformations. As an example, for a numerical set, we may be basing normalizations on a set's mean and standard deviation. Or, as another example, we may base the methods for a categorical column on the set of values found in the data. For the logistics of extracting these properties, we have a few options for how to handle the different datasets, such as for distinctions between training, validation, or test datasets. One way would be to just handle each set separately, such as to extract separately between training data and validation data, and simply apply transforms on those two sets on each distinct basis. The problem with this method is that this may result in an inconsistency of transforms. For example, the mean of the values found in the training set may be different from the mean of the values found in the validation set. Another way to go about extracting properties for the basis of transformations could be to just lump all the sets together in evaluation. For example, we could evaluate the mean of a column, including both the training and validation data in aggregate. It turns out this approach also has a problem in that it can lead to what is called data leakage, by which we mean that when we go to train our model, some of the properties of the validation set will have leaked into the training set, which means our validation assessment could overstate the model's accuracy score. Automunge offers a solution to both of these problems by basing the transformations for all sets on the original properties derived from the training data. By using the same basis for all sets, we are ensured of consistency of transforms, and by not including any of the validation data for the derivation of these properties, we are ensured that no data leakage will take place between the training and validation operations. Oh, and as an added bonus of this method, by removing the need to assess properties of data prior to transformations for the test data, we end up with a much more efficient means of preparing that data, which may translate to energy efficiency or even reduce carbon intensity for processing streams of data at scale. The Automunge platform includes a built-in library of feature engineering transformations, fully documented in our README available on GitHub. We found it helpful to organize the transformations based on the intended data types of target columns, such that we've aggregated between categories of numerical target columns, sequential target columns, such as for time series data, categorical target columns, and some really neat stuff for date time data. Each of these sets then have a few sub-aggregations of categories. For example, with numerical data, we have several types of normalizations available, including z-score, mean scaling, min-max scaling, and a few variations upon each. For sequential data, we have a few methods of taking first, second, or even higher order derivatives, such as may be useful for bounding cumulative data, for instance. For categorical sets, we have several means of encoding, including one-hot encoding, ordinal encoding, and some really neat binary encodings, which is actually the default. Our date-time methods allow a user to segregate entries by timescale and apply sine and cosine transformations to address periodicity, as well as aggregating bins for various traditional boundaries, such as business hours, weekdays, and holidays. Oh, and I'd be remiss not to highlight that categorical sets can also be further processed with string parsing methods, such as to extract numerical portions of an entry or even identify character grouping overlaps between entries. This is a very useful part of the tool for automating what might otherwise require manual extractions of data. Let's give a few examples of what these data transformations are actually accomplishing. Shown here is a simple data set consisting of 3 source columns of what we're calling raw data, each with 3 entries. The first red column is a numerical set, which could be populated with floats or integers, for instance. The second white column is categorical, showing with string entries of 3 colors to demonstrate. And then the third column is another categorical set, this time with only 2 distinct values in that set. First, for the numerical set, we'll demonstrate 2 different kinds of normalizations. The 4-character strings, shown here of NMBR and MNMX, are actually how the transformations are accessed when assigning transformations to distinct columns. The README documentation contains a full catalog of the available transforms, each with their own 4-character string designation. Here, the NMBR string refers to a z-score normalization procedure, in which the data is centered around 0 and scaled by the standard deviation. Another kind of normalization available is for min-max scaling with the MNMX transform, which scales data within a range 0 to 1 based on the maximum and minimum values found within the set. This one might be useful for cases where we want to ensure that all of our return values are non-negative, for instance. These are just 2 examples. We have a whole catalog of various normalization methods along these lines. For categorical sets, we'll demonstrate here a few of the methods available. The TEXT transform is what we call our one-hot encoding, which returns a distinct column for each category found in the set. Here, 1 column each for the entries of red, white, and blue. If you want to encode a categorical set in a single return column, we could use the ORDL transform, which is an ordinal or integer encoding. And then somewhere in the middle for memory bandwidth is the 1010 transform, a binary transform that allows multiple column activations for reduced memory bandwidth. We also have a second kind of binary transform, intended for cases where the source column has only 2 distinct entries, designated by the BNRY transform, which encodes a single column of zeros and ones. Oh, and it's worth noting that these four-character strings that designate the different types of transformations are also generally appended to the column header titles as suffixes, such that the column header titles of the returned datasets log the steps of transformation by way of suffix appenders to these header titles. Although the basis of the tool is that transformations must all originate from a single source column, there's no need to limit our transformations to a single application for each source column. Using a set of what we call our family tree primitives, which I'll defer to the documentation to describe, it's possible to specify generations and branches of multiple transformations. Such as, for instance, if we wanted to present our features to the machine learning algorithm in multiple configurations of varying information content. Here's an example of a numerical set with 3 different returned configurations to be presented to the training operation. First, a version with min-max scaling, and then the other 2 configurations derived by the output of a power law transformed, followed by both a z-score normalization and a set of bins based on number of standard deviations from the mean. Of course, if we have infinite training data, there may not be much benefit to presenting feature sets in multiple configurations. But for cases where we have limited training data, these type of operations in some cases may make the extraction of properties in our training operation more efficient. Another example of multiple tiers of transformations originating from a single column is given here for a source column of a sequential data stream, such as some time series data or a cumulative counter. In this demonstration, the data stream is presented to the machine learning algorithms in 3 configurations. The first is the raw data with the simple z-score normalization applied. The second derived by first taking a dx over dt, or derivative value, based on some time step, followed by a z-score normalization, thus returned a normalized calculation of velocity. And then the third return set derived by applying a second derivative operation after the first, again followed by a z-score normalization, here providing some estimate of acceleration of our data stream. These demonstrations have been for cases where a user assigns sets of transformations to distinct columns. It's also important to keep in mind that alternatively, preparing our data for machine learning with the Automunge function is possible even with full automation. For cases where a user does not assign distinct methods of transformation categories to a column, the algorithm assigns its own transformations based on an evaluation of dataset properties to infer appropriate means of numerical encoding and infill. Thus, it is possible for a user to pass raw data, and the algorithm automatically returns numerically encoded data with infilled missing values, such as to meet the minimum requirements for the direct application of machine learning. The feature engineering transformations are not the only automated methods to prepare the data. Another common obstacle for real-world datasets is that our data streams may have instances of missing or improperly formatted data points. Consider here a numerical set in which can be found a NaN point, which stands for not a number. Or perhaps may contain instances of string entries, which are inconsistent with the desired numerical formatting. Traditionally, a data scientist has several options for how to infill missing points, which may include replacing these values with values derived from the set, such as a mean, median, mode, or maybe replacing missing values with an arbitrary integer such as 0 or 1, or another method could be just to copy the value from an adjacent cell. The Automunge platform allows a user to choose any one of these methods for assignment to distinct columns, or a user may just defer to the automated default methods. Under automation, each category of transformation has its own default infill method. Another option for the automated infill of missing values is a really neat method that we refer to as ML_infill, which basically means that infill values are predicted using machine learning models trained on the rest of the set in a fully automated fashion. We'll go into a little more detail of the ML infill methods here. The dataset on the left represents our raw data, segregated between purple shading for features and orange for labels, which may include instances of missing or improperly formatted values, here designated by the red X's. The ML infill method takes this data, sets aside the original labels, and then from the feature set partitions into subsets, which serve as training data and labels to train a column-specific predictive model, as well as feature sets corresponding to the missing points, which are applied to that trained model to predict infill, which is then inserted in place of the missing values. Another really useful built-in method that we want to highlight here is for purposes of evaluating drift of dataset properties between the original data used to train a machine learning model, which was prepared with the Automunge function, and subsequent data used in inference, which was prepared with the postmunge function. We actually have by default that when data streams are prepared in the Automunge function, distribution properties are derived for each source column. This includes distribution properties based on the raw data that was passed, as well as those properties evaluated along with each transformation function applied. Then, when it comes time to prepare additional data with the postmunge function, by activating a simple parameter, those same properties are evaluated to generate a comparison report. This type of analysis may be useful, for instance, to determine when it is time to retrain a model based on drift of dataset properties. Continuing our exploration of additional push-button methods built into the library, another really neat method is available for evaluation of feature importance by making use of what is known as the shuffle permutation method. In this method, the raw data is prepared with the Automunge function and then is used to train a model with an evaluated accuracy metric. The feature importance metrics are then derived by, for each source column, randomly shuffling the data, such as to dampen the accuracy of the inference operation. Then, by comparing the original model accuracy to the inference accuracy after the shuffle operation, we can derive a metric which gauges the importance of the feature that was shuffled. Automunge actually has expanded on the traditional shuffle permutation method by incorporating a second importance metric, where the first metric measures the importance of the original source column, and the second metric measures the relative importance of each feature derived from that same source column. There's more. Another useful push-button method built into the library is for purposes of dimensionality reduction of our training data. We actually have two options here. The first making use of principal component analysis, or PCA, which is a type of unsupervised learning in which the columns are collectively transformed, such as by aggregating to a reduced number of axes. And of course, the subsequent application of the trained PCA model to data is automatically performed in the postmunge function. A second type of dimensionality reduction available in the library makes use of the feature importance evaluation. Here, the feature importance metric is evaluated for the set of columns, and dimensionality reduction is performed by simply dropping a designated range of the low scores. This may prove useful in cases where a user is uncertain of the applicability of various information streams to a problem. However, it should be cautioned that in cases of highly redundant data, single column scores may be impacted. Another neat push-button method is for purposes of label engineering. Label smoothing refers to the practice of updating the activation values of a one-hot encoded label set to a reduced threshold for activations and an increased threshold for nulls. As shown here, we've set an activation metric of 0.9, and then the null values are derived from the number of remaining categories. Label smoothing serves the purpose of allowing a training operation to account for the fact that there may be some improperly designated values, or noise, in the labels, and so has the effect of allowing the model to recognize that there is some uncertainty associated with the training data. Automunge actually has extended the traditional label smoothing operation to add a little more intelligence to the null activation values, a method we refer to as fitted label smoothing. Here we see that the null activations in a fitted smoothing preparation are tailored to the number of activations associated with each column. Although not an extensively tested hypothesis, the expectation is this method may offer some further improvement to probabilistic calibrations. Continuing our exploration of the dataset preparation options, yet another push-button method worth highlighting is for purposes of preparing datasets for oversampling during the training operation. Oversampling is a method to address cases of label set class imbalance, which just refers to when we have an unequal distribution of the different entries in a label set. Shown here is an example where we have 4 ones and 2 zeros. This is an example of class imbalance where the zero values are underrepresented, which may dampen our model's extraction of properties from those zero labels. When it comes time to train our model, a simple solution to this problem is available by identifying the underrepresented labels and performing a copy and paste operation, such as to append additional copies of the underrepresented labels in order to better balance the examples. What's really cool is that Automunge doesn't just offer this method for categorical sets. Numerical label sets, such as for a regression problem, can also be treated with an oversampling preparation by aggregating bins from the data, such as, for instance, the number of standard deviations from the mean. At its core, the Automunge platform consists of 2 simple functions. The Automunge function accepts NumPy arrays, or pandas data frames, and prepares raw data to a form suitable for the direct application of machine learning. A user may apply sets of data transformation functions from our library to distinct columns for purposes of feature engineering, or may alternatively defer to automation, allowing the algorithm to infer appropriate means of normalizations, numerical encodings, and infill. The function returns these processed datasets along with a simple Python dictionary capturing all of the steps and parameters of transformations. This return dictionary can then be passed to the postmunge function along with any subsequently available data to easily, efficiently, and consistently prepare data for training or inference. Think of Automunge as a method intended for integration into the workflow in the step immediately preceding the application of machine learning to tabular data. And when you try it out, please be sure to let us know. Oh, and don't worry, we didn't forget, we promised some special effects for this video. Are you ready? Here they come.